the first thing to talk about is actual signal flow. So we're all probably, most of us on this, probably not everyone will remember the analog days where signal flow was what you saw. You directly plug things into a socket on a device you wanted it to go into a channel. You'd insert some outboard on a particular channel, and then you'd take an output off a particular output at the desk and send it to an amplifier you wanted. And it was a very easy thing to see the signal flow. An example of a CADAC installation that wasn't one of ours. Sadly, no one on this call who knows what that is. But you could physically follow each cable and see what it was doing. And then along came some digital stuff. And in the beginning of the digital stuff, it was still the same. You had analog inputs into your desks mostly, and then everything after that would be AES or MADI. And with AES or MADI, it's still point to point. So signal flow is still followable. A physical cable that goes into a device, another cable comes out of the device, back to the desk as an insert, so with the TC at the bottom, and then AES out to your amplifiers. The only real difference is you had more channels down a cable than with analog. Analog is one signal, AES on XLR is 2 signals, and MADI up to 64, depending on sample rate. But it was still a physical flow. Sort of said some things on here, so examples of old digital links, AES, MADI and ADAT, they were all point-to-point connections. Signal flow was very obvious. Nowadays, with network audio, it's very different. We're still dealing with sampled audio data. Not going to talk much about sampling, but does everyone understand the basic concept of digital audio with sampling? So we take an instantaneous snapshot of the voltage, the analog voltage, many, many times a second, 48 kilohertz, meaning we take it 48,000 times a second. We take a snapshot of the analog voltage. Everyone okay with that as a principle? So we end up with digital numbers, 48,000 times a second, telling us what's going on with the audio signal. But with network audio, we still have sampled audio data at a particular sample rate, but we're no longer really point to point. Each channel of audio can be routed to any device across the network, and you don't have to route all the channels between devices at once. So device A could send 1 channel to device B, 3 channels to device C, etc., etc. It all becomes a bit virtual, all becomes a bit like the cloud. You put data out onto the network, and then devices pull off what they need, which particular audio channels they need. So now, no longer does our physical wiring represent the signal flow. So from a design and build point of view, what this means now is we no longer have to put equipment in the same places. So here's a simple little drawing of some data flow. It all goes up into the network. So you've got RMIO input units on the left, which is a Yamaha input stage rack that takes analog and AES signals and outputs Dante. It goes up into the network, and then we've got a CL5, which is a digital Yamaha mixer, which has Dante 64 in, 64 out. And we know about DS10s, most of our shows, that convert Dante to AES, and then that goes into DMB's amplifiers, as they have no direct AES input, but like an L acoustics amplifier or various other manufacturers in some Maya stuff have Dante straight into them. So when we were designing of racks and locations of equipment with analog, we had 3 constraints. The first one, and this constraint stays mostly through, is where do you need to have it so you can control it? So anything with a front panel control, you need it to be near you at front of house if you need to be able to operate it. And if it's a piece of radio equipment, you want it near you so you control the front panel. But then there was another constraint that came in very quickly, which is we wanted things to have the simplest and shortest cable paths between them. So that governed where we chose to put equipment. And then also we would think about, well, if a piece of equipment connects to many other places, we should put it as central as possible between all these other locations. So each link is cut down to the shortest length cable. Now, if a piece of equipment has no remote control, you would choose to put the equipment where it needs to be controlled from. Nowadays, most outboard equipment you can remote control. So TC6000s has a remote interface. Amplifiers have remote interfaces, which is basically your XTAs from the old days. So not only can we now not worry about physical audio wiring, we don't worry about control either, because it can all just sit on a network. So now we can choose to put equipment wherever we have space. This means we can end up with smaller front of house areas because we can remote any equipment that doesn't need to be there. It can be routed substage. Often this has better access in front of house racks, which are often tracked by audience, a little bit of light, and you can get to them during the show. So it's sometimes nowadays a good idea to put equipment where we can get to it the most. And now that means we definitely end up with equipment not in locations related to its signal flow. So there's unfortunately, as with all things network, there's various different standards out there, and the number of standards is ever growing. Go back quite a while, Yamaha, I think it was Yamaha, developed EtherSound, which was a packet-based network. It wasn't true IP. It was very proprietary. It was limited to 100 megabit links, but it was point-to-point. So it was basically like a MADI link, 64 channels over a piece of Cat5. So it didn't really advance this cloud mentality of audio networking. Then came along another group of networking products. It started off mainly with Audiante, who's the company, so you sometimes hear that name. Dante is the name of the standard that we all use. And these had great advantages, and still do. They're single standards. So Dante and Ravenna are single standards. They're closely controlled by the manufacturer of the product. So Ravenna controls their protocols, Dante controls their protocol. And the hardware that is connected to their networks is made by them. Every Dante product in the world has the same chipset connected to the Ethercon connectors. Even if the boards are manufactured by the end user, so Avid or Yamaha, they have that circuitry and that control chip and that audio chip have all been made by Dante. And they make standard boards for manufacturers to introduce. This means it's incredibly controlled protocol, so it's very reliable. We'll come back to this a bit later, but they've both now migrated to support AES-67. AES-67 is not a full standard, but it does describe methods of communicating audio over networks. By different manufacturers of digital audio networking supporting AES-67, it means we can route audio between different manufacturers now, which was a huge problem before. If you had audio on a Dante network and audio on a Ravenna network, you would have to convert both to MADI to be able to link them between each other. Nowadays, they're starting to make ways to link different systems together. However, if at all possible, we should always try and just use one protocol on our shows per show. You may not have heard of Ravenna, I didn't say this. Ravenna, Dante's very much taken over the live audio market, very, very common. Ravenna is incredibly common in broadcasting, certainly in Europe. I'm not sure about the US. It has slightly different specifications. Both Dante and Ravenna are layer 3 messaging, which means they use IP addresses to send their data. So every device has an IP address, and that's how data is forwarded. And they're quite happy to work on any data rate of network, whether that be over copper up to 1 gigabit, or if we've got fiber linking with 10 gigs, they'll work up there because they basically conform to Ethernet packaging. The last category, which started off with AVB, and you may have heard of the Milan group, came a lot later than Dante. And actually, AVB is not a fully developed standard. It just says you should do things in this sort of way. And the other part about it is it doesn't provide any common definition for how control interfacing should work. So how, from your software, how do you discover what AVB devices are on the network at what addresses? None of that is prescribed in the AVB protocol. So that's why most manufacturers haven't adopted it. And indeed, you probably all know that Avid consoles use AVB to transport between stage racks and the console, but because it's an Avid product talking to an Avid product, it knows exactly what address it's going to find the other device at, how to discover it. Avid came up with their own way of checking their device exists. But because there's no common standard, other manufacturers' equipment plugged on an Avid network wouldn't be able to see any devices. This is where Milan's come along, and a lot of manufacturers have got together. I believe Avid, Meyer, L Acoustics, D&B, and there's several more. And they basically said, well, AVB's got us 50% of the way of a usable product. Now, why don't we as a group standardize how we're going to communicate over this network? And that will eventually mean we will be able to connect a DS10 directly to an Avid console. We'll be able to connect a Meyer product directly to a DS10. it's the plan, it's where they're going, but it's not there yet. Milan is still very much in development. Differences between Milan and Dante and Ravenna. Milan and AVB require managed switches because they have a very, very precise clocking and a very precise way of achieving that. They work over layer 2, so they're using MAC addresses, not IP addresses. And again, their network speed is not really limited. That's kind of just a little bit of a background to some of that. So what do we need from our network audio devices? Well, we're still doing samples. We're still sampling data. So we need to have a way of sending a clock around the network. A lot of us will have heard the term of word clock, which is how we did it with AES signals and various other kind of interfaces. Word clock was a signal that sent when to take a sample. So it was a very precise waveform that told each device, this is exactly the moment to sample, so that we sample evenly. What's very important in digital audio is that we have a consistent time between samples. If that varies, then effectively it changes the instantaneous frequency of anything making a sound at that point, and you get all kinds of artifacts. So accurate samples, where each device takes a sample, more importantly, the gap between samples has to be incredibly accurate. So we used to use word clock, which was its own signal. Most of us would have done it over BNC, and that's how we linked our digital devices together. It would be very nice if that could happen over the network. What else do we want from our network audio? Well, we would like a way to send an audio channel from one device to an input channel on another device. And that's going into our networking terms, the unicast method of sending the data. A channel on one device to a channel on another device. So it goes from device A to device B. That's unicast, one-to-one. We also might like, spelled multicast wrong. We also might like to send one channel of audio to many end devices. An example, certainly in the rock and roll world, where they do less matrixing, they might have 30 amplifiers just for their left array. They want one signal going to every one of those amplifiers. So you would be patching 1 to 30. So it might be more efficient to do a multicast way of sending that message at that point, i.e. you send from one transmit out and then the network switches forward it to all devices, and then you're only having to use one piece of data. We also, from our network audio, we want to allow the user to configure how this channel sending works. We need a way of setting up the network, what talks to what. We'd like to see an overview of the audio across the network, and we've got to deal with different latency problems due to network hardware, etc., etc. Here's a little diagram I nicked from somewhere that sort of shows the differences between the two setups. So Dante, AS67, QLAN, and Ravenna all are based on legacy Ethernet stuff. So from the MAC address downwards, so the MAC address down to the physical electrical characteristics of cables and optical, etc., is fixed, and they've just built control on top, and there's two sections, actually delivering the audio, and then the next part's configuring the audio. Where AS67 is lacking is it tells you how to send audio, but it doesn't tell you how to configure the different devices on the network. Milan is built on AVB, which is much lower protocol. Because I'm going to mainly talk about Dante, I threw in a random fact that Ravenna has a limit of 768 channels bi-directional, 1 gigabit link, 48K. So I'm going to do a little quick chat on AVB and Milan, just so we can understand some of the differences to Dante and also understand some of the problems with timing and latency. Sort of said some of this already. Protocol, yeah, because AVB isn't a defined standard by one company, it's incredibly open to opinions, hence Milan came along. I think I've actually said everything on that page, so I'll leave that for another day. So what's special about AVB is it works by reserving bandwidth across the network path that it wants to send audio. And when I mean network path, say device A goes to one switch and then onto another switch and then onto the end device, it will reserve bandwidth through each of those links. So that's 3 links. On typical non-routed networks, i.e. unmanaged switches involved in your network, you cannot reserve bandwidth at all. On managed networks, you have to have a switch that knows how to manage bandwidth, which is where we get these special modes of AVB on network switches. So if we think about a 1 gigabit link between an AVB device and a network switch, an AVB protocol can say, I can reserve up to 75% of that link's capacity. It chooses, it tells it how much it needs, but it has a maximum limit of 75%, which means it can reserve 768 megabits a second just for its use, no other device. To enable reservation bandwidth, your switches have to behave very differently. Normally a switch will try and deliver all data, first that arrives, first that it sends out. And on all managed switches, you can configure a kind of priority system depending on types of messages, a bit more on that later. However, if suddenly data arrives all at the same time, and they're all at the same priority, we have a problem. On AVB compatible switches, and they're more expensive, the Luminex now has a mode where you can enable them to be an AVB mode. They allow this special reservation of bandwidth. So there's mainly two types of data systems on networks. Audio data is incredibly predictable. We have fixed sampling rates, so we know how many channels we're going to be sending between devices once we've configured our system. So we know how much data will move between each device per second. We can calculate it. The network can calculate it. We can predict how many data packets they'll be sent and when within each second that packet will arrive and need to be sent. So if we look at a small example, 48 kilohertz sampling, which I think we all understand, and we're only sending one channel of audio. And imagine for a moment that we would send a network packet every time we've generated a new sample, which might be one system. And if we're using 24-bit sampling, so you've probably all heard of 8, 16, 24 bits, how many bits are used to the resolution of how much data we keep of the analog signal. That is 3 bytes. But all network packets have header information. They need to know, as we've learned, destination and source MAC address, destination and source IP address, what type of message it is. And actually, if you're doing sample-based data, you actually need to know which sample number it is so that the packets can't, if they get out of order, the receiver can put them back into the correct order. So all in all, a 3-byte sample of actual payload audio data would need around 50 bytes of network data, not very efficient. So what most things have decided to do is it's better that the transmitting device takes several samples, storing the results, and then sends them out in bursts. Now we don't want to wait too long because each packet, for the length we delay a packet, that adds, for the first packet, that adds latency into the system. A lot of people have chosen to do 32 samples per actual packet of data they send across the network. And if we look at this, 32 samples, in our one channel example, 32 channels, 24 bits, that's 3 bytes, that's 96 bytes of data. With 48 bytes of header, that's now 144 bytes. It's a lot more efficient because we've only had to send one set of header data instead of 3. What is really important, and I don't know if we spoke about MTU before, is we have to keep all audio network packets below this magical size called MTU, which on most devices is 1500 bytes. And that's a switch and Ethernet limitation. They actually route all packets based on that size. So in our example, we're saying, well, we're going to store 32 samples. At 48K, that's only a delay added of 0.66 of a millisecond. So absolutely fine. But as with all things digital, latency adds up. So every part of our system accumulates delay. And that's one part of it. If we do this system of only sending a packet every 32 samples, then we would send 1500 packets a second at 48K. What would be really ideal is if the other network traffic used the time in between these packets to send their data. Because the audio data is going to happen precisely and regularly, every time we've taken 32 samples, we're going to send the data. That's a very precise rhythm. There's huge gaps in between that in networking terms, and it would be really good if those gaps were filled with other data. This is fundamentally how AVB works and what it's done. They've split the network time almost like a bit like TDM, time division multiplex, for those that know what that is. And that's why you have to have special switches that can work like this. Most of the rest of the data on our network is not predictable. It's what we would call burst traffic. So an example is VNC. VNC, apart from mouse and keyboard, sends the changes of pixels on a screen. So if the pixel doesn't change on the screen it's transmitting, it will not send any data. So if you've primarily got a screen that's not changing what it's showing, so e.g. a QLab screen when no queues are running, nothing is changing on the screen, VNC sends very little data. However, if I suddenly minimize QLab and expose the desktop, suddenly we've got to send every pixel on the screen. That's a big sudden burst of data that will go on the over the network, and then it will settle back down to low data again. This isn't predictable. And so on a normal network, it could suddenly start sending all this burst of data, and that would delay audio packets that were arriving whilst that burst is happening. And on AVB network, that can't happen because it's forced to have these slots. Same with OSC messages and R1. The other thing on our networks that is very predictable, however, are radio receivers. Most of them send out 20 samples a second, snapshotting audio level, RF meters, and LQI. So that is predictable traffic. Everyone all right so far? Cool, cool, cool. I think said most of that. For some people, it might be easy to think of. In the UK, we have this annoying traffic lights at some junctions that bus lanes get priority. So as soon as a bus arrives, the lights change and it allows the bus past. And then it lets the normal traffic back. That's exactly what happens on an AVB network. As soon as it's due to send an AVB packet, it halts sending other data briefly, sends the AVB data, and then gets back to sending the data. So if we look at it on an AVB term on our networks, now Luminex support AVB, we can use those. We've got three things at front of house, the S6L, R1 and QLab, and we were trying to put them all over the setting network, which we wouldn't do. In this case of the S6L, talking in terms of its AVB data to the engine, as you can see top right. As you can see, the S6L is sending its data uniform length and at precise time gaps between them. R1, it's taking small amount of data fairly regularly as well. But QLab, because we're VNCing, not any data, and suddenly a huge burst. And then if we line those up time-wise bottom center, you can see that this audio packet would get delayed on a normal network. As you can see here, that gap's equal, and then the end result here is it's been knocked on and delayed. On an AVB network, however, it would choose to stop briefly sending this VNC update, put the audio packet in, then go back to the VNC update, then there'd be another audio packet, and then it would finish the VNC update. Does that make sense to everyone? Ones that I can see, cool, cool.
Sounds good.
So that's where AVB is quite different to what we're going to talk about with Dante. It provides very low latency because it's incredibly predictable. So therefore the network doesn't have to put in buffers on receiving devices in case data's not arriving quite on time to be able to smooth out these time gaps. Also, we haven't talked specifically yet, but clock signals have to be part of this reserve bandwidth, so our word clock type signal. And we need this to cross the network very precisely and very quickly with low jitter. By jitter, I mean the gap between each message arriving is the same. And this enables us to get very good phase accuracy of audio samples between different devices. You'll often hear people who prefer AVB over Dante say that whilst every device plugged into one stage rack on a Dante network would be in phase, so if you could put the same signal into all 32 inputs, they would perfectly sum. Between stage racks, between Dante devices, they are not phase accurate. So if you split a drum kit or anything else that you want to do close timing on across two stage racks, they will not be phase accurate on a Dante network. But on an AVB network, they are. Every stage rack takes that sampling point precisely. So moving on to a network that we all know, well, we've all used quite significantly. So Audiante manufactures a Dante. They keep it very close to their chests, how they want to do everything. Every manufacturer has to buy or have certified the Dante interface part of their product. Audiante makes several versions of their Dante interface card. The most common one is Brooklyn 2, currently most common one. And this allows any audio product that a Brooklyn 2 card is in to the audio product to transmit and receive 64 channels of audio in each direction. Dante patching, i.e. how we decide which device receives which channel of data, is done using their own program called Dante Controller. And they've dealt with redundancy. So all Dante products have two network ports, primary and secondary. They always transmit the same data as each other. Receiving wise, if the network's behaving and everything's working properly and there's no faults, every device will receive the same data on primary and secondary. And each device will use data from the good receiving port. It will stick on primary unless it has a problem. what this does mean is if you have two completely independent networks, one for primary and one for secondary, so everywhere you have a switch for primary, you have a switch for secondary. If any single switch fails, the data is duplicated on the other network by the product. So end to end, we do not lose audio. And it is a sample accurate changeover within a device between the two networks, providing there's no funny timing going on. One other feature of Dante is if you decide that you're not worried about redundancy, is the two ports can be changed into what's called daisy chain mode. So in this mode, it becomes a way of having a network switch on your rack. You can loop through it to the next rack, to the next rack, to the next rack, and they still act as one network. Every device can still see each other. What's really important is you set this mode the same on all devices before plugging them up. Otherwise, if one device is in daisy chain and connected to two different switches, it causes chaos. For very low channel counts, Dante can absolutely work over using unmanaged switches. You don't need to use managed switches. The main thing that prohibits some switches is if they have EEE mode, which is the green energy saving mode, which is where switches sort of fall asleep if they think they're not that busy and don't send data out as fast as possible. So that's a good thing to turn off. On a managed switch, we turn that off, and on an unmanaged switch, if it has it, you can't do anything about it. So that's sometimes what prohibits unmanaged switches. Once you start getting into significant channel counts, and by significant, I personally think we're sort of talking over 128, then you really should be using managed switches because they have a lot of features, as we'll get onto, especially for clock routing, that make them superior. Instead of like AVB, which uses network switches reserving bandwidth, Dante has two other methods of ensuring its data arrives in a timely manner. We'll come on to some of them later, but one of them is actually on network switches, there are multiple queues of data. We'll look at that a bit later. And the only thing we have to do though, unlike AVB where the AVB device tells the network how much bandwidth it needs, we have to think about how much bandwidth we need to make sure is available to Dante if we're sharing that network with other network traffic. A little summary from our Brooklyn card down the bottom here. So now we'll come on to what flows is in a second. A flow is 4 channels of audio. So for a Brooklyn board at 48K 24-bit, 4 channels of audio would take up 5 megabits per second out of our 1 gigabit link. So not very much at all, but you could see how it grows pretty quickly. Similarly to AVB, because all network messages need around 50 bytes of header information, sending small loads of data is very inefficient. With unicast data transmission, which is one device to one device, which is the most common in Dante, to make this transmission efficient, Dante have come up with 2 things. So as we sort of mentioned earlier, they send more than 1 sample per packet, and Dante's the same, it's chosen 32. But they've also declared each packet must contain 4 channels of audio. And if you do that at 48K, that's roughly 500 bytes of data in each packet. Now, if I only want to send 1 channel of audio from Dante device A to Dante device B, it still sends that 500 byte packet. It's still sending data for 4 channels, even though I'm only using 1. It just sends 3 magic silent channels of data that are ignored. So one flow, and the other thing to think about with flows is in unicast, 1 flow of data can only go to 1 other device. And this is the reason I'm laboring this is there's a strange limit in Dante, because each Dante device is limited to how many flows of data it can achieve. And the limitations of a flow is each flow has 4 channels of audio, but a flow in unicast can only go to 1 other device. So why is this important? Let's look over the next few slides. The last line I think actually does help. Every receiving device uses up at least 1 flow from the transmitter. So Brooklyn 2 cards support 32 flows. So you'll be thinking for a second, well, hold on. Brooklyn 2 card is 64 channels in, 64 channels out, and the flows are 32 flows in, 32 flows out. Well, if it's got 32 flows, then that means it can support 128 channels of audio. It doesn't. What it means is we can send copies of that audio to more than one device. So if we have a Dante device, we can connect a maximum of 32 other receiving, apologies. A transmitting Dante device can connect to a maximum of 32 receiving devices. So if we want to send audio from one device to more than 32 receiving devices, we can't do it as unicast. We have to have another thing because it only can do 32 flows. So it can only talk to a maximum 32 different devices. And then if we did connect one transmission device to 32 receive devices, each of those devices would maximum only be able to get 4 channels of audio. However, those 32 devices do not need to get the same 4 channels of audio. Each of them could have a different one. So device 1 could have channels 1, 2, 3, and 4 from the transmit device, and device 2 could have channels 2, 4, 5, and 6. They don't have to be sequential. Another combination we can do is that we can connect one Dante transmit device to 2 Dante devices and connect all 64 channels. A flow is 4 channels. To connect all 64 channels, we need 16 flows to go from device 1 to device 2. That leaves us 16 spare. We can do the same again. Or we could have some combination in between. Does that start to make sense on flows? Sometimes this can be hard. Got a few pictures though, so maybe these will help if people are confused. So inside our device, say whether it's a CL5, a DS10, an RMIO 64D, whatever Dante device, with a Brooklyn 2 card, inside the box, 64 channels of audio go into the Brooklyn card, 64 channels come out the Brooklyn. That's how it works under the hood. Great. Then going out onto the network, we can transmit 32 flows each of 4 channels, receive 32 flows of each of 4 channels. Just a note, because some people get confused, you do not double your channel count by primary and secondary working differently. They mirror. They both do the same job. If they're in daisy chain mode, they are the same network. And if they're working as redundant mode, where they're both separate networks, they mirror each other. You can't use them to double up the number of flows. So let's look at a little example of a little small, tiny Dante network. We've got 2 Rio racks, which are Yamaha analog input-output units. And we've got 2 CL5s on our network, which are Dante Yamaha devices. And we're just looking at inputs from the stage rack to the CLs. And our CL5A here, it wants to get channels, sockets of audio 1 through 7 from the Rio rack, Rio 1, and it wants to get the same sockets from Rio 2. So it wants 14 channels of audio data from the network. CL5B, it wants different channels. It wants sockets 9 through 18 and socket 22 from Rio 1. And from Rio 2, it wants channels 1 through 13. Again, can't do the math off the top of my head, 9, 10, 11. That is 24 channels. So let's look at it from the perspective of Rio Rack 1. So CL5A wants channels 1 through 7. Okay, well, output flow 1 from Rio Rack 1, it's going to send that data to CL5A, point to point. And in that flow, it's going to put channels, its input channels 1, 2, 3, and 4. Great. But we also need 5, 6, and 7. So we need a second flow, which is going to go to CL5A. And that flow is going to have channels 5, 6, and 7. And then the 4th channel in that flow is going to be unused because we only need the 7 channels. Then looking at the data going from Rio Rack 1 to CL5B, we're going to have a 3rd flow out of Rio Rack 1, which will go to CL5B. So IP-wise, it will route to CL5B. And it will send channels 9, 10, 11, and 12. We need also more channels, we're all the way up to 18. So we'll do another flow, which gets it 13 through 16. And then we do another flow, which gets us 17 and 18. And then the last 2 would be unused. So in this example, we've wasted 3 paths out of the Rio because we don't need them. And it doesn't matter, we're nowhere near our 32 flows. But this is where flows can become a problem on high channel counts. If we now look at it from the perspective of CL5A, its incoming flows, so data coming in from the network, its first flow will come from rear rack 1, channels 9, 10, 11, 12 from rear rack 1. Second flow would be channels 13, 14, 16. Third flow would be 17, 18, and 22. And one not used, great. Then it would start.
Hey, Russ,
Yes.
is the flows issue why we have to use the digiface?
Yeah. Wait 5 slides.
Okay.
But yes, this issue crops up in a few places. Yeah, and then continuing on, it would allocate its input flow 4 from rear rack 2, so on and so on. I've laboured the point enough, but hopefully that helps explain flows from both ends of the cable. In general, though, we don't have to worry about flows, other than what Gareth just said. Dante Controller, the program we use to patch and configure the network, takes care of sorting this out. It takes care of putting different channels from each device into different flows, all for us. However, it is possible to run out of flows without technically having got to the channel count because of the limitation of one flow only goes to one device or wasted channels within a flow. If you can end up in a position where and Dante Controller just reports to you, no, I can't make the connection. But it will tell you you're out of flows. So that's why you can have a different number of channels you think you can get across the network than you actually can. Commonly, this problem occurs when you're taking only 1 or 2 channels in from many, many devices, or if you're sending a couple of channels out to many, many devices, e.g. main left and right, 20 amplifiers aside if they were on Dante. Dante Control tells you out flows. If you're doing an output that needs to feed several devices, then it might be best to turn one of these flows from unicast mode, 1-to-1, into multicast flow. But we'll look at that a bit. So multicast enables you to send one flow to many devices. So that would get around our amplifier problem. If you're doing multicast flows, then that is when you definitely should be working on a managed network. And we have to, most of the time, have to get into multicast management, which some people will know as IGMP snooping. Very fun acronym there. As Gareth has kind of already got onto, so the Brooklyn 2 is a hardware card. And for those of you a bit nerdier, the card talks to the audio device using TDM, the TDM lanes of audio data, the 64 channels of audio into the device physically in the box. When we connect computer playback, we're all used to plugging a sound card that was a USB or Thunderbolt sound card into a computer. And so we would think it's logical to plug a Dante sound card into a computer. So plug its USB or Thunderbolt in, and then on the other side of it, it would have network ports that behave as a Brooklyn card or something like that. And indeed, various people now, it wasn't very common, are making devices that do that. RME, in this little picture here, make a Digiface Dante. In actual fact, it doesn't have a Brooklyn card in it. It has a different one of their cards and can actually support 128 channels of audio in and out. And it supports 64 flows in and out. Arguably, this is the best solution because as far as the computer is concerned, it's just another sound card. You would configure QLab or whatever you're using to talk to sound card called Digiface. Great. And then the Digiface would appear on our network, get 124 orders, as I just said. And if you kind of do it this way, you're guaranteeing low latency as low as the software, your playback software can handle. Now, the reason we talked about that is there's another method of doing Dante from computers called Dante Virtual Sound Card, or DVS. It appears as a little applet program, little snapshots of it there on the right, very little information. You have to license it, and you can configure how many channels it's using. And I think you can go from 4 in, 4 out, up to 64 in, 64 out. Now, we'll get onto this in a bit later, but every Dante device, we set what the maximum latency we think we're going to encounter for crossing the network is going to be. And on most devices, we set that at 0.5 millisecond, just fine. Dante Virtual Sound Card, the lowest you can go is 4 milliseconds. So that's something to bear in mind. And the only other option you have on Dante Virtual Sound Card is to tell it which network interface on your computer to send the Dante traffic in and out of. It's a very, very good idea to always use the motherboard network interface for Dante. And any adapters that you plug in, e.g. Thunderbolt to 1 gigabit or USB Ethernet adapters, to keep those for your other network traffic in and out of that computer. The main reasons are that the motherboard network interface is much, much more stable and gets a higher priority to the processor. However, once you've run this application on your computer, it now generates a sound card as far as any audio applications are concerned, and you can just route your sound card to Dante Virtual Sound Card. I think I've said most of the things on that page, apart from, as Gareth said, the thing with Dante Virtual Sound Card is it's limited to 16 flows. So remember what we just learned, 16 flows means we can only connect a Dante Virtual Sound Card interface to a maximum of 16 Dante devices, whether that's input or output. So if we think about radio receivers and WaveTool, so WaveTool, we're commonly and all modern radio receivers have Dante out of them now. So quite often we'll take our Sennheiser 6000s, which are 2 channels per box, put them onto a Dante network, and then put that into a computer where WaveTool will then treat that as a sound card and move on. I certainly got caught out earlier on with this 16 flow problem. If I have more than 16 receivers, I cannot connect them to the computer using Dante Virtual Sound Card. So even though Dante Virtual Sound Card can handle 64 channels, I can only connect 16 flows. Each flow coming in can only have 2 channels of audio because I have a 2-channel receiver. So I'm wasting per flow 2 channels. That's why I'm stuck with only being able to get 16 receivers into Dante Virtual Sound Card. And the solution to that is to put something like the Digiface in, which can handle 64 flows. So then you get around that problem. However, something like the Axion system, which has 4 channels of audio per receiver, would work absolutely fine because that's 1 flow. I can use the full 64 channels. That was your thing, wasn't it, Gareth?
Yes, yes, it was.
This slide sort of says most of what I've just said. However, my last point on the bottom, DVS actually also takes away processing power on your computer. Not much, it's incredibly good. But if you're pushing your computer very hard, if it's working as an Ableton Effects rack or many other high processing audio devices, you really are better putting an external sound card. If you want, so Digiface, if you want to go to Dante, than trying to use DVS, because a hardware interface does a lot of the clocking and timing stuff in the interface box and not in the computer. So it takes far less CPU to process. So it can be quite efficient. If, however, you're playing back a couple of tracks from QLab, no worries. So I briefly mentioned the different topologies. So each device has a primary and secondary port. However, if we set them to be in daisy chain, we don't get redundancy, but you can chain through each device and they'll appear on the same network. The negatives of doing daisy chain, and I don't think we would ever do it on anything we're doing, is if that middle Rio failed, you'd lose everything. Because the far Rio wouldn't be able to see the desk at all. They don't bypass the network when they fail. So no network device bypasses the network when it fails. So we tend to do it as redundant. And so in our topology, we'd connect all the primaries together, all on one network. This would be a typical signal flow on if we were using Yamaha. And we could have more than one switching path. It doesn't matter. We treat it like a normal network. And this is actually what we're doing with 2 switches for every location, one for primary, one for secondary. This is not a loop in terms of networking, because the 2 networks don't actually physically connect together anywhere. And that's really important. So we don't have to worry about spanning tree stuff, as we talked about at the end of one of the things. And if any single device fails, whether that's a network switch or a hardware device, all of the other devices will work just fine and the show will continue. And in actual fact, most people would be unaware of a failure of a network switch in this condition, because only Dante controller would report to you that bits of the network have lost half of itself. The audio would continue, so you'd be almost oblivious. So we have to, very, very importantly, one of the first things we have to do when we get a Dante device is tell it whether it's working in redundant or daisy chain mode. Now, on most things, you do this through Dante controller. However, Yamaha, which quite a lot of us touch quite a lot of Yamaha equipment, they actually try and do some of the Dante configuration from the front panels or the back panel of the devices. So on Yamaha products, most of them with Dante, you configure daisy chain or redundant mode using a dip switch. I think on nearly everything it's dip switch 4 according to their manual. So Yamaha make it nice and simple. We don't have to plug in just the primary, to go to Dante controller and check that it's in redundant before we connect anything else, but a little bit more on that in a bit. If you go back quite a long while, the only redundancies on most shows was a second power supply for the analog console and maybe some UPS for computers. We actually had quite an interesting conversation the other day with a few of us about what we think is the best topologies for certain things, because quite often introducing changeovers between one system and an alternate system, the changeover is still a single point of failure. So it can be quite hard to work out what best to do in redundancy. Dante make it very simple, in that they provide 2 ports to do everything, and it was a very clever decision in the beginning. Pretty much all this stuff says. So let's talk a little bit about clocking. Just excuse us 1 second. So just as most of us are used to in digital desks, and before we were doing networked digital audio, we were doing any AES audio or MADI, everything had to be in sync, and we would have to have a device called a clock master, and we would distribute that clock to every other device, and that would keep everything sampling at exactly the same time. Now, within Dante, it does each Dante device on the network, other than Dante virtual sound cards, so all hardware devices, can all act as the clock master. However, if you want to sync your entire Dante network to a word clock signal, then you would put that word clock signal into one of the Dante devices that receive Dante, so Yamaha products, some of them you can put word clock into, and then you'd have to set that device to specifically be the Dante clock master, because that would then sync the Dante network to the word clock. However, most of the time, we're running our Dante networks free, i.e. there's converters in and out that do sample rate conversion or something else, so we don't need to worry about the Dante network being in sync with any other network. As long as all devices on the Dante network are in sync, that works fine for us. So Dante network has its own method of deciding who is the master, and that method is purely based on MAC address of the product. If we want to, we can choose which device we think is more reliable, or the device that would always be switched on first, so the network doesn't keep reconfiguring itself. Certainly on shows that I'm involved in, I tend to tell the network to let the RMIO 64Ds, which are the MADI Dante converters between the console and the Dante network, be the clock master, because they power up within half a second of getting power, and they're on pretty quickly, and they talk to the desk, so it keeps the clocking world all happy. Once a device on a Dante network has been chosen to be the master, all devices will clock from it. If that device fails, however, immediately the network elects the next suitable candidate to take over. So you end up can get Dante clock switching happening all the time without realizing it, and no problems, no audible problems, because they seamlessly take over from each other. From a networking perspective, the Dante clock data are multicast messages. So they, on an unmanaged network, because they use a particular range of IP addresses that we looked at ages and ages ago, they tell each switch just to forward that message to every socket. On a managed network, we can control that, but we want to ensure that that particular multicast message is allowed to all Dante devices. Otherwise, we get weird clocking. If we've mucked up on a managed switch how we've set up our multicast settings, then you will end up seeing in Dante controller that there are multiple masters devices active on your Dante network. If that happens, you've got a problem with your multicast routing settings in a managed switch. In most scenarios, we don't need to filter in switches multicast routing. So if you have ended up in this situation and we're in the shops and you're trying to work it out, grab an unmanaged switch that's not EEE and start working back through until the network comes good and you see one master. It's a very good indication of a multicast setup problem. Because there are different latencies around the network, each network switch has a propagation delay, and some Dante devices might have to go through 3 Dante devices before they get to another Dante device, for example, or so and so. Each Dante device chats back and forth with the device that's been declared the clock master. And by sending messages stamped accurately with time back and forth, the device can work out how late the clock is arriving at it. So what the propagation delay is across the network for that clock signal. Each device can then counter the clock arriving late and then all the clocks will come in exactly the same time across the network. But because of this method of clocking, that's how come we don't get phase accuracy between devices. So within Dante, anyone who's done any Dante setup, you will have noticed there is a latency setting. And the reason we have this option for latency is all Dante receivers have buffers. And that means they can receive data and they'll store it for a short amount of time and then we'll send it on. Now we, of course, want everything to be sent on at precise time intervals. The most important thing within a networking terms is that audio packets have equal gap, exactly the same gap between each packet. Now, on a network, you can't guarantee that a packet won't get delayed slightly more than another packet. And it ends up with this problem that the best solution is to timestamp each, because you have a master clock, you timestamp each packet and then send it across the network, and then the receiver will delay it for the difference of the latency time. So what do I mean by that? Look at the next slide. But normally on a Dante network, we would choose a latency setting of 0.5 millisecond or 1 millisecond. It lets you choose 0.5, 1, or 5. If you're using 5, something is really wrong with your network. But this method of setting what the maximum latency is enables the buffers to be set so that we can realign all packets to even time, exactly the same gap between samples. So let's look at that in a bit more detail. Say we've set all our Dante transmitters to 0.5 millisecond latency. Nice and simple. We've got a scenario here where we have two devices that are two Dante devices transmitting, but one of them is going through another switch compared to the other one. Each switch adds about 0.1 of a millisecond of latency, roughly, depending on its traffic that's running. So already, assuming no other data is holding up the audio packets, Dante A data will be 0.1 of a millisecond later than Dante B. But because there's not fixed bandwidth allocation, data can get held up if a switch is transmitting other data briefly on that link. So it can get delayed more. Both Dante A and Dante B transmit their data at precisely the same time, each sample, because they're kept in track by the clock, and the fact they can work out how late they're receiving the clock means they have the same clock as each other. So they both transmit at the same time, but they're going to arrive at a different time. So we know that we've declared the maximum latency through our network is 0.5 millisecond. So let's look at it from the perspective of a message from Dante A to the receiver. So a flow message leaves Dante A and arrives, after 0.3 of a millisecond, say, at the receiver. So 0.1 is it's going through two switches, that's 0.2 of a delay, and it got held up slightly further along the way. The receiver will look at it and say, well, I'm going to delay everything to have a latency of 0.5 millisecond. That's what you've told me. You so far have only been delayed by 0.3 of a millisecond, just getting to me. Therefore, I'm going to delay this message by another 0.2 of a millisecond. And that now means the total delay has been 0.5 millisecond. That's the concept. So it will constantly look at how long it's taken to get to it, subtract it from the maximum latency setting we've chosen, and put the difference in. That means if this next message from Dante to the receiver gets to the receiver in 0.4 of a millisecond, this next message would only get delayed by 0.1. So it's evening out the variable delay across the network. If we take another example of, say, from Dante B to the receiver, the message takes 0.15 of a millisecond to get from Dante B to the receiver. Therefore, the receiver is going to delay it by 0.35 of a millisecond. So it's standardizing the latency across the whole network to the same delay. And that's accounting for each path having a different delay and having a slightly variable delay. It corrects for that in this mechanism. So that's how we get things back in time and in phase. Does that make sense? If I've not explained that correctly, someone ask questions on that, because I'm not sure I have. But feel free to ask. No? Okay, cool. So maybe you can now see the problem. If we've told our Dante network that we know you can definitely get every message, the maximum delay you're going to find anywhere in the network is 0.5 millisecond. And the receiver is compensating anything that arrives early, perfect. But the receiver can't compensate for anything that arrives late. So if a packet gets delayed by a lot more than 0.5, now we will get an audio artifact. It's late. It can't make it any earlier. So now that will give us a pop, a click, or a bang. Now, if this happens, the reason you can choose between 0.5 millisecond, 1 millisecond, and 5 milliseconds is to deal with this problem. But in all reality, the Dante controller actually gives you an analogy against each time and says, if you're less than 4 switches, you've only less than 4 network switches in any path, use 0.5 millisecond. If between 20 and 4 switches in any path, use 1. They give you an idea based on, switches can delay. Realistically, if you're using any more than 1 millisecond, you have a problem. There's either not enough bandwidth for your network, or you've got a routing problem, or you've got a conflict, something else is going on. In general, on all of our shows, we should be able to run within 0.5 millisecond because we're no more than 4 switches across the whole Dante network normally. Dante controller does report all of this timing. So we can look at that in there. And indeed, it reports very strongly if a packet arrives outside this latency window that it can compensate. Yeah, everyone good with that? It's actually quite a common problem. And I make it a particular point to look at the latency reports in Dante controller, especially during like the first week of production on site. And I'll do it in the warehouse.
Really possibly cool. A silly question, but does a managed switch, is the latency within a managed switch any different from a non-managed one?
Not measurably, unless you've done something with a lot of rules or things that we really shouldn't be going into.
Sure.
But it can be. And it normally can be as if a lot of people, when they're doing layer 3 routing, which we don't do, can get into a mess where packets are delayed by a long time. So yeah, you can do.
Thanks.
In general, unless you need to use a managed switch, you shouldn't. But realistically, our Dante channel counts nowadays, we have to for clocking mainly. Cool. Everyone okay there? Excuse me. So one thing we haven't talked about is IPs and IP addresses. So I sort of said earlier on that Dante uses IP addresses to send the data. It knows that it's same as we've talked about with all the other devices all the way through these talks. It will say, I need to, this Dante device over there that I want to send data to is 192.168.3.40. I'll send the data packet to there. And then the network switches look at the IP address and say, oh, I know where that is. It's on this socket on this port on my interface, and I'll send the data out. But most of us will never have configured an IP address on a Dante network, and that's for a good reason. But the first part of it, we've got to remember that every network interface needs a different IP address. They have to be unique. And that's whether they're on the same network or not. If there are two network interfaces on the same device, they both must have different IPs and be in different subnets. We've seen that earlier on. Otherwise, the computer or the audio device doesn't know which way to send the data. On a device, Dante primary and secondary ports have the same data. You can specify fixed IP addresses on Dante devices, and you would have to specify an address for the primary and address for the secondary, and they must be in different subnets. However, just like with any part of networking, any single mistake in setting a subnet or setting an IP address would cause chaos. And honestly, most of us, once it gets to the actual real world of digital audio, we really just need it to work, and we don't want problems to try and track down. Dante controller, the main reason we've talked about in the past needing to know what IP addresses devices are using is A, we can know what their address is so we can log into them and configure them. And B, knowing their address means we can do network tests to find them and see if they're behaving correctly. Because Dante has made their own discovery mechanism where the control program doesn't need to know the IP address, all the Dante devices advertise themselves on the network. They have a kind of, hello, I'm called this, and I'm an IP address 169.254.3.1. And Dante controller receives that message and says, oh, now I know that for a Dante device called DS100A, you are 169.254.31.32. Great, and it remembers that. So because it has this mechanism and it reports all the data, we don't need to know the IP addresses of these devices. So we can allow Dante to do what Dante does, and it uses zero config. Now, we talked about zero config a few weeks ago, but just to remind you, zero config is a mode where a network interface makes up its own IP address, and it chooses from a range that's allocated for this special mode. And that range is 169.254.0.1 all the way through 169.254.255.254. And the subnet of that is not what I've written there. It's 255.255.0.0. Damn it. I'll fix that before I send it out. And then on the secondary network, it does the same thing, but it has to be in a different range. Now, the Internet Protocol only defines one block of addresses for zero config, where the device makes up its own address. So what Dante have done is they've chosen another range that's part of the addresses allowed for private networks. So in theory, we could use that space, 172.31, but we don't, especially if we're doing Dante. We know that that's a Dante thing. And in general, certainly on all our world, we use the 192.168 part of the IP addresses that are free. In both these cases, their subnets are 255.255.0.0, not what I've written there. I will fix that. Sending the slides out. And this happens automatically. But also just remembering back to the zero config thing, it is possible for the IP address to change between boots. So every time you power on the device, it's possible for it to choose another address within these ranges. But because it advertises itself on the network, Dante controller finds it. We'll come on to how audio still carries on working with it in a minute. So let's have a quick look at Dante controller. Most of us have probably seen some of this. The first thing that's most important to do is to set up Dante controller, which runs on a Mac or PC, and tell it which network adapters, interfaces on the computer are on the Dante networks. Now, from a fault finding point of view, I strongly recommend that one of your Dante controllers, if you're running a couple, depending on what you're doing, can see both primary and secondary networks. So that means you have to have at least two network interfaces on that computer. Now, the reason for that is there's a few fault conditions on a Dante network that only get reported on their own network. So if some problem occurs on the secondary network and we're only running Dante controller on the primary network, there are some fault conditions that will not get reported to us. So invariably, I think that's the same in Andy. We try to make one of our system computers at front of house have both networks available. So we would have at least 2 network interfaces. And one of those network interfaces would have an address beginning 169.254, and one would have 172.31. Now, some people might question me on that in a second. So the way you get to this Dante config is in the bottom left, you see the P&S lights. And the green light shows you've got a good network connection, one on primary, one on secondary. If you click on that area of the screen, this window pops up. Now, currently, when I took this snapshot, I had it connected to my home network. It's defaulted to connecting to my home network, which, as you can see, it's given itself an IP of 192.168. That is not the network that was doing Dante. So I had to change the network interface to the other one. And a good way you can tell you're on the right one is it should have the right range of addresses. As we sort of just said on a previous slide, all devices, if you set them to being a computer, if you set a computer to be DHCP on a network interface, that's where it expects to have a server to talk to tell it an IP address, and it doesn't find a server, which it won't, because we don't do those, then it will zero config its address. So if you're using a network interface for primary, it will, if you set it to DHCP, it will automatically give itself an address of 169.254, because that's what internet interfaces are designed to do. This interface we want to use for secondary will also give it, if you don't give it an IP address, will also set itself to 169.254. something. And this then won't be able to talk to the secondary network properly. So what we have to do, did I do it on this? So what we have to do is on whichever interface we're using to talk to the secondary network, we have to set a fixed IP address. I tend to choose 172.31.0.1, the first one in the range, and set its subnet to be 255.255.0.0. And at that point, you should be able to see both networks. I'm not able to run that at home, so I haven't got any snapshots showing you the 2 connected. So once that's done, you should get back there 2 green lights bottom left, but for the 2 networks, you should say it should see them. And then it should start filling up in the main window Dante transmitters and Dante receivers. Now, most devices are transmitters and receivers. All that means is that any device that outputs audio will appear in the transmitter section along the top, and any devices that are capable of receiving Dante audio will appear down the left. And then this turns into a giant matrix where we can route channels, a transmit channel to a receive channel. Now, you can also have problems where a particular channel can't route correctly, and that's when you get these little hazard symbols. When these little plus buttons expand them to show all of the channels, when they're collapsed, if any channel has an issue, it marks a hazard over the whole device, as you can see there. That's the basic. So this is with some tabs expand. So up the top, I've expanded my DVS that was running on my Mac, and you can start seeing a list of all the channels, 1 through 32. And then on the left, I've expanded the DS100, and that's its 64 receiving channels. And now we can just patch channels between them. Click on a square, get a green tick as it's routed. Now, all of the ones that I've routed have got green ticks. Then there's these hazard symbols that appear under the name, but not against any channels. When it's like that, it means this channel, this receiver, is patched to something that can't find on the network. So it's patched to something that's not this device, and it's not on the network, which is a nice way to help us fault find. Let's just look at some routing. I think most people are familiar with what's showing there. So that's telling me that input 36 to the DS100 can't get its audio signal that it's expecting to be able to find, but 31 through 35 are good, and nothing is patched to 30. So that's our matrix. That's how we route signals. Very, very simple. So sort of already briefly touched on this. Under the hood, Dante is using IP addresses to actually send the audio data. That's how the network switches know what to do with the data. We know now that it uses static IPs using zero config most of the time. And these could change between each power up. So if the IP address changed, if it's stored, oh, I get my audio from 169.254.10.10 channel 3, that IP address could be different next time we power the system up. So that's not a good way to remember the routing. Instead, receivers remember patches by name. So you name each Dante device. And then when the network starts up, each Dante device announces its name and what its IP address is. It's now IP address. And the receiving device knows what name it's looking for, and as soon as it sees this advertising of what the IP address now is for that name, then it can make the connection. So a receiving channel will remember that it was connected to a device. Let's have an example. So it knew it was connected to a transmitting device called RMIO 64-1. If you have many RMIOs on your network, they all have to have unique names. So -1 for unit 1, and it was connected to channel 2. When our receiving device next gets powered up, it looks for RMIO, a Dante device advertising its name as RMIO 64-1. If it sees this, it will then take the IP address that's being advertised, and then it will talk to that address and say, hey, I need a flow from you, and I would like channel 2 in it, please. And that's how it reestablishes on a power-up. This has a good advantage for if you have to replace a Dante device, because if you set the new device's name to match exactly the old device, when you power the network back up, all the receivers that wanted a signal from the replaced device will connect straight away with no problem because it uses the name. So you wouldn't have to sit and repatch. You name the devices in Dante controller other than Yamaha products. And I didn't do a slide for this, and I should have done. On Yamaha products, they have a rotary switch that's labeled 0 through F. And what Yamaha's done is they've tried to make their system as plug and play without needing Dante controller. And under the hood, so if we have a RMIO 64 and we set it to 1, it names the Yamaha's device, names the Dante device within inside itself, Y-001-RMIO 64. And it's got the 001 because the rotary switch is in position 1. If I move that rotary switch to position 2, it would change the name of that RMIO device on the Dante network to Y002-RMIO 64. And it does that with all of its products. So CL5 with switch in position 1 on the Dante network will be Y001-CL5. It's just a faster way with that Dante controller. When we're in the shop and we're starting up, if the show has four RMIO 64s, when we've given them a hard reset, they'll all have the same Dante name, apart from this switch. It was a bad choice. But most Dante devices with reset have the same Dante name. So when we're starting to configure our Dante network, it's really important to turn on one device of each type at a time, go into Dante controller, name it, and then turn on the next device and name it. If you do turn all four on, you will see all four in Dante controller, but you won't know which is which. Some Dante devices you can, in Dante controller, click identify, and that makes the lights, the Dante lights on the front panel blink with the device, so you can slowly work through which one's which. So you can name them so they're all unique. All good there for people? Cool. So on my particular example, the reason I had some good and bad patches is the DS100 Dante card receiving ports on it have remembered that some of them were patched to a different device, and that happened to be my PC DVS. So that's why we got the error. Now, looking at more details in Dante controller, we've got the 5 main tabs at the top of the program. So we've been looking at the routing tab. If we go to device info, we get a brief summary of all the products on the network. I only had 2. Because actually in a DS100, it's a PCIe card. It's a Yamaha Dante card is actually what DNB put into their DS100. So it comes up called PCIe for that card. That's its default name. I can see what firmware of Dante it's running. It's this particular DS100 is rather a long way behind. I can see what primary address it's allocated itself, and the same with my Mac on its Dante virtual sound card port. And we can see that they're connected to the network using 1 gigabit links. And we can see that in the case of the PCIe card, it doesn't have a secondary address and the link's down. And that's telling me it's not connected. That's a good fault finding thing. And in the case of Dante Virtual Sound Card, you cannot connect to both networks. You can only ever connect to primary. If you double click on one of these rows, you expand and you get much more detail for the device, which is what I've done here. So if we double click and expand, and in the top center, you choose which device you'd like to look at if you want to change it. So we're looking at the DS100 here, and we're looking at its receive ports. When you look at its receive ports, it helpfully tells you where each channel on the receive is patched to. So channel 22 receive is patched to channel 30 from my PC, which it currently cannot see. Also has a speaker symbol, which is again quite useful for fault finding. If there's any audio running on that channel, it should hopefully blink or be lit in green. From here, it's also at the bottom summarizing how many input flows have been used up. So for the patches I've made, I've used 6 out of 32. Quite a useful tab, and we can fault find from that why it thinks there's a problem. You can also name each of the receive channels, but I find that very quickly gets out of sync in a production process and much rather not doing it myself. You could put, if you've got a very large fixed Dante network, maybe naming things like this is amplifier input left 1 or left 2 or left 3 might be useful to you if you're doing an installation. Moving along the tabs, this is the transmit tab. The transmitter doesn't know, or does know where it's sending the data, but it doesn't report it in Dante controller. Again, if a Dante transmitter is receiving audio from the actual audio device, this light lights up, quite good for working your signal flow when there's a problem. And again, we can name the channels if we want to. And it does tell us how much of the flows it's used up over here. Status, not much useful on this tab, to be honest, but it does give us an overview and a quick picture of only one network interface connected. Here's the latency tab, which is quite, I personally ensure that I monitor, certainly both in the shop and in the early days on site. So this is looking at things from the point of view of the receiver, because only the receiving Dante device can know about the latency, because it's only after it's received it does it know how late the message is. For each transmitting device it's connected to, you will get one of these charts on this page. What do I mean by that? Take my DS100 here. If it's actually receiving audio from RMIO64 Unit 1 and RMIO64 Unit 2, so it's receiving audio from 2 devices, I would get 2 histograms. And it would tell me RMIO64 1, this is the histogram, RMIO64 2. For those like me who had to look up when Dante first came out what a histogram was, it is telling us how many packets have arrived at which latency. So along the bottom here is milliseconds, 0, 1, 2, 3, 4. Now this is Dante Virtual Sound Card, so 4 milliseconds is the lowest it will go to. So this being the big is fine. Most shows we'd be seeing 0. You'd always see the maximum number at the end. We'd be set to half a millisecond. So you'd be seeing 0.1, 0.2, 0.3, 0.4, 0.5. Against each 0.1 of a millisecond, or in this case, half a millisecond it's doing them in, it shows us how many packets, how many flow packets have arrived at that time. So it's had 10 packets have arrived, whatever that is, 1.5, 1.2, and a few packets 1. This is maybe this logarithmic, because you end up, if you're on for an hour, you end up with thousands and thousands of packets. So the next one would be 1,000. And what that enables us to see is that most of the packets are arriving in that time. And over time, these bars would grow taller and taller and taller. And as long as that's well below, or, well, strict definition, as long as that's below the maximum latency we've set, everything is happy. I personally, you should be seeing it no further than 2/3 of the way up the chart, because then you have a little bit of leeway for packets to get delayed by unexpected network traffic. But this is showing me that all the packets from my Maxis DS100 are arriving on average within 1.1 milliseconds, so around a quarter of the maximum latency we've allowed, so everything's great. If it was to be drawing bars after 4 milliseconds, we'd probably be hearing it. If it was only 1, we wouldn't, but if it's several, we would be hearing it. And these bars are drawn in red. Anything after the latency time are drawn in red, so it's pretty clear you've got a problem. But this is something I actively monitor and implore people to do when they're setting up Dante networks. Does that make sense to everyone? Sweet.
Yes, sir.
Moving along these device tabs. This is the device config tab. This is where we can actually change the name. So if we come in here at the top there, I could change that name, then click apply. Don't be impatient at that point. It does take about 5–10 seconds for it to refine the device and enable you to do any more work. That's perfectly normal. You can set the sample rate that the Dante interface is running at. This really, most manufacturers don't let you change this piece of information. It's locked to whatever the audio device is, which makes sense. I think I may have skipped over on an earlier slide. On a Dante network, you can have devices running happily at different sample rates. However, you can only patch devices together that are running at the same sample rate. So it's perfectly fine to have 3 devices communicating between themselves at 96K and everything else communicating between itself at 48K. You just cannot make patches between those devices. There's no sample rate conversion across the Dante network. If you need to achieve sample rate conversion, it has to happen within a device. This is where we set the latency that we want this device to run at. So I've chosen 1 millisecond for anything connecting to the DS100, but I have nothing here. Encoding is for, you'll certainly see things like Dolby devices and all of that, different encoding algorithms. Again, not really something we get into. The final tab is Network Config tab. Now, this is where on most devices you would set whether it's redundant or daisy chain. If you're on a Yamaha device, you won't do it here. You'll do it on the dip switch like we talked about. If Dante Virtual Sound Card doesn't have primary and secondary, so you don't need to worry about it. But anything else, you have to do this. And you have to do this before you connect both Dante and secondary on a device, sorry, primary and secondary on a device to their respective networks. Because if the device is configured as daisy chain and you connect it as primary and secondary, you will take the whole Dante network down and it will all stop talking. So I, again, in a warehouse perspective, tend to start one of each type of device up at a time and only have the primary switches with power. I leave the secondary switches unplugged so that I'm only seeing one network and I can configure them before risking chaos. This is also where you could set manual IP addresses if you want to. Certainly in the scale of events that we do, or certainly that I do, there's absolutely no need, and you really are best off letting Dante do its own thing. They are manually configurable, but they don't always quite work as you'd expect. So a little bit more information on the clocking. We've seen that Dante accepts higher latency, so small variable network delay is okay. However, this has to remain a small number. Otherwise, we're going to get over delay on our networks, and any delay in audio is bad. We want to know our delays. Now, we saw that AVB has a system of reserving bandwidth. Dante has a different approach to trying to manage its signals, and that's to use quality of service messages. So Ethernet, and this is something that's built into Ethernet. Ethernet enables messages to be tagged with a priority number. And within managed switches, they can deal with 4 priorities. So any incoming message on a VLAN gets added to one of 4 queues, depending on its priority settings. This is a mode called Quality of Service DiffServ mode, which is reasonably common, but it's what you have to use for Dante. You have no choice. QoS DiffServ, before Gareth gets any ideas, can only be done on internal networks, and all ISPs override any DiffServ message data added to your network messaging. So you can't do this over the internet.
Yeah, you clearly knew what I was thinking there.
Yeah, beat you to it. It's like I've worked with you for X years.
Yeah, right.
These 4 queues are numbered 1, 2, 3, and 4. Top priority queue is number 4. So the way the switch works is on a given VLAN, when it's next ready to send data, process packets out, it will look at Q4, and any messages in Q4, it will deal with every single message in Q4 before it even looks at any messages in Qs 3, 2, and 1. As soon as Q4 is empty, it starts processing messages in Q3, then it looks at Q2 and Q1. It's not the time for making jokes about different classes and all of that, but it is like treating things with different priorities. This piece of information is stored within each packet of Ethernet data. And this is down to the Ethernet device to set which priority they want the message to do. Actually, what they do is they define a message to be one of 64 types. These types are fairly random. There's no real definition. And then within the switch, we set each of these 64 types to which queue they go into. As far as Dante is concerned, there's only actually 4 types of messages. So we want Dante wants us to set the highest priority for any messages that relate to clock. So it's going to allocate a particular class type to any clock message, and then we have to tell each switch that that class must be treated with the highest priority. The second it has time to deal with it, anything in that queue gets dealt with. Dante then says we have to set all audio messages to be priority 3, and the remaining config and discovery messages priority 2. If we're using Dante with unmanaged switches don't have a priority system, and it works just fine. The only reason we have to start worrying about this on bigger networks is when we have more data flowing. We need to tell it what messages are most important. And when it comes to digital audio, what's most important is the clock. Audio data isn't quite so important because we have these latency buffers, but the clock has to be precise, as fast as we possibly can across the network. Now, Luminex have done another great trick here. It's one tick box on a Luminex. You just say enable P2P. I think most Luminex switches now say P2P version 2 on the VLAN, and it will then do the rest. P2P is another lovely acronym. It's called Precision Time Protocol. And version 1 of that protocol is what Dante uses. Ravenna uses version 2. The 2 versions can coexist on the network, but they don't communicate between each other. However, on a Luminex, setting P2P V2 being enabled on a VLAN is all you need to do, and it does 1 and 2. They just don't say that it does 1 and 2. On our friend the Cisco switches, we have a couple more steps. So unfortunately, back into switches. Along the left-hand side of most Ciscos, you'll see a menu for quality of service. And the first thing on quality of service properties is we want to put it into mode basic. We're not looking to configure all of our options here. And then we go down to, in the tab basic mode, we go down to global settings, and we want to use the mode called DSCP. Apply that. So far it's all nice and easy. And then this is where it gets confusing. So the black numbers on this list are these different classes of messages. There were 64 defined, 0 to 63, because it's computer. And you give each one of these types of messages a priority. Now, unfortunately, you just have to know these or look it up in the chart. Yamaha and Shure both have great facilities. If you literally type in Yamaha Dante QoS, you instantly will get a picture of this on a Yamaha PDF, so you don't have to remember it. Or indeed, you could have it in this document. And the ones we have to remember, I should have highlighted, but I didn't get time. Class of message 56 is a clock, it's the clocking. And we give that a priority of 4, highest priority. Class of message 46 is audio, and class of message 34 is config and address information. And that's all we have to do to set up quality of service on a Cisco. So it's not too bad. Where are we at time? Might skip to here and then come back. To be honest with you, the next thing's quite a big subject, and it might be easier for me to do it next time, to be honest. The next step, which I suddenly realised was quite a lot of information, was talking about how to do multicast configuration, which is where you send lots of one message to lots of destinations. And Gareth also wanted me to talk about ACL rules, which is how you configure, you can filter messages on managed switches. So it's a bit of an odd time to have got to this point, so I'm sorry about that, but I think it would take longer. Is there any questions I can help answer from here? Or anything people want to go back over?
I've been watching people on the video, Russ. They've been very quiet, but they're all paying attention.
Yeah, no doubt.
Russ, I've got a really random one.
Please.
So if you're clocking over AES, what's the physical interface that allows that to happen behind the connector?
So on systems where you don't connect word clock, which a lot of us got used to not bothering with, because in theory every signal, any digital signal should be clocked the same. When you say clock from AES, what you're actually doing is every time it's...
I'll have a 99.
Huh? All right.
I'll have a 99 if that's all right. You get them all in?
Yeah, no problem. Except they're not 99p anymore, are they? You can derive a clock signal from any digital signal. Because on an AES signal, it'll always start sending, in theory, start sending the sample data precisely at the start of each new sample point. You can actually derive a word clock from it.
Right.
And most devices have a way of deriving a word clock from a digital signal. So whether that be AES or MADI.
Russ, has that got anything to do with PTP, which I don't really understand what it means, but I learned about it the other day?
P2P is what we're talking about here with Dante clocking and Ravenna clocking.
Right.
It stands for Precision Time Protocol. And it's just another network protocol that enables data to be sent across the network and be able to work out the lag. So you can work out, P2P is just how you do audio clocking over network. It enables timestamps to be sent, and then when you send a message back and forth, you can see what the latency is on that message, and you can work back to what the actual clock is.
And am I right in saying that some switches are PTP compliant and some aren't, or is that not how?
It's absolutely true. So Luminex give it to you as a nice little option, P2P. All P2P version 1 messages tag their messages with a class of DSCP class of 56. So we can tell a network switch, a switch that doesn't necessarily know about P2P, managed switch doesn't know about P2P, to just high priority any class 56 messages in diffserv. And that means P2P messages get priority because they all use a class of 56. So all P2P is a way of devices on a master on a network sending out a regular clock, but then the remote devices, by receiving that clock, adding its own time to it, then sending it back to the master clock and then receiving a message back again, it can work out the latency. And at which point it can adjust its internal clock to be in sync. So Luminex make it lovely and easy by it being one lovely tick box. You just turn on P2P. If all we really need to do to make that work on a Cisco is turn on diffserv, QoS, and make class 56 priority 4. And then all P2P messages get the highest priority across the network. And obviously you need to do that in every switch. What context were you looking at it in, Reece?
Oh, I was just doing a course the other day about sort of AES 67 and some other little bits, and sort of what was it, ST? I forget the numbers, 2110 and stuff like that. And just looking at all that, and I didn't quite understand what he was on about when he was on about P2P switches, so I did a little bit of research. But
yeah, that's what it is. It's just a switch that makes sure those packets get the maximum priority. And AES 67 sort of basic level standard to enable things to communicate digital packets. So it has to define how clocks work. And it uses P2P version 2, whereas Dante uses P2P version 1. So if you're trying to link a Dante device to an AES67 device, you have to derive your clock from a device that can have the AES67 standard, because it then outputs P2P 1 and 2. So both halves of your network are okay.
Right.
It's very dull.